Hello, everyone, and thank you, Bernard, for that nice introduction to the topic. I'll give you a very brief overview of our paper that's in the special issue, with written with my colleague from UC San Diego, Andrea Chiba. So next slide, please. So this is one of the main figures in the paper. Gives an overview of what we mean by neurobiologically inspired self-monitoring. And on the left side of that cute little robot are the brain areas that are associated with self-monitoring. And on the right side would be some examples from robotics and autonomous systems. And I'll go through briefly each level, but uh, at the lowest level, you have lots of sensory motor information, and I want to just uh, point you to some of these arrows. So the sensory information goes up to an intermediate level, which I'll give more information, and provides, like Bernard said, anomalies in unexpected outcomes, system state, and then the top levels predict outcomes and do error correction, and then all the way down to the bottom to set points that would be expected. But the thing I want to make clear is there's a lot of interaction, even though I have this hierarchical levels, there's a lot of interaction between these levels, both in the neurobiology and what we would suggest for self-monitoring, self-awareness systems in engineered systems. So next slide, please. So just to go through briefly each level, at the lowest level, you have sensory and motor primitives. So in the nervous system, this is carried out by the periphery, the spinal cord, does a lot of heavy lifting of just day-to-day movements, and it does it very rapidly, and many times below the level of awareness. And if you have robots or autonomous systems, you need certain things that you just are givens, like motor controllers that when you send a command, the wheels move or the arms move. Sensory systems that do some level of processing. So when you ask for sensory information, you don't just get raw data, you get something interpretable. But another important thing that's not always talked about is having innate values and preferences. So any autonomous system has some sort of built-in preferences to maintain connectivity and ensure health. And on the right was one of the first robots I worked on called Darwin 7, and that had innate preferences. If you look at its fingers, it had taste buds in its fingers, and it preferred highly conductive metal objects and did not like weakly conductive metal objects. And it had this affinity to approach any sounds or bright objects. And so the reflexive was good and bad tasting to it, but then it used the sounds and sounds and sights and vision to actually predict what was good and what was bad in its world. So if you go to the next slide. So at the intermediate level, we have basically monitoring the self and in the internal systems. And a lot of times it's called homeostasis. So you're trying to achieve some level that's healthy for the system. You know, whether it's hunger, thirst, your heart rate, or with engineered systems, battery level, heat. There's also the concept of allostasis. So that means that these set points can change, and you want to predict what they should be and then set a new set point for your homeostatic system. And to give an example from robotics, if you look on the right, this is work from Cully, Moreau, and Clune. And this was a self-monitoring robot. It was a legged robot, and it could detect when one of its legs were broken. And then what was interesting about this was it did this form of allostasis. So it did some self-modeling in its robot brain, tried out different things, predicted what would be the best new gait given the injury, and then was able to adapt very rapidly to overcome this injury. And next slide, please. And at the highest level, there's this cognitive control. And in the brain, we think of things that are cognitive, like attention, executive control, decision making, strategies, planning. and even emotion. Um, the problem with this is it takes a lot of time to develop and apply. So it's critically important for those intermediate and lower levels to rapidly handle events, maybe without awareness. But then if they are important, bring it to the awareness of the cognitive control level. And just two examples, there's more in the paper of what's at cognitive control, learning and memory and effective behavior. So learning and memory, if you look at the robot on the right top, that was one of our robots that had a memory model based on the hippocampus interaction with the frontal cortex. And without going into all the details of the brain, but these areas actually could do some rapid learning and also put things into context, which we called schemas, so that if you were in a new context, in this example, it's in a classroom, the robot was in a break room or a cafeteria, it had expectations of what objects would go with different contexts. So that overcame catastrophic forgetting. And given that it had sort of a prediction of what it should expect in these different contexts, it was able to do few shot learning. So this is an example of using a neurobiology idea that actually could solve some problems that are with machine learning and deep neural nets. On the bottom right is work by my colleague Andrea Chiba's group, and that's looking at affective behavior. So emulating emotions can allow robots, intelligent systems to be more natural in their interaction with humans, but it can also lead to awareness of your own self and others. And in this nice example, there was a rat and a couple of robots, and the rat was in a trap, and one of those robots actually let the rat out of the trap. The other robot just ignored the rat. And when the robots were in the trap, the rat helped the robot that helped the rat before. So it monitored not only itself, but had sort of this empathy of who was helpful to me. Um, and so that can be applied also to autonomous systems, especially when you get to the interactive systems um, that are going to interact with people. Yes, and the last slide, just to kind of go over overview, some of these organizing principles of the nervous system can be applied to embedded systems and Internet of Things, self-driving vehicles, and our work in robotics. Um, and the nervous system is monitoring the self at multiple levels, making predictions of what to expect, setting different expectations dynamically is very important. Um, and if something becomes important, it gets kind of heightened to the level of self-awareness. And we believe like following some of these models could lead to more autonomy and just more flexible behavior. And hopefully you can have a chance to read the paper in full, and I'll answer any questions that come up during the chat.